So let us recall what we did in the previous lecture. We have discussed that under the continuous function, the Cauchy sequence will not be preserved. That means f is a function from x to y, which is a continuous function. And if you have xn is Cauchy sequence in x will does not implies f of xn is Cauchy sequence in fx. This is not true. We have seen the counter example for that. Also, we have seen that if x is complete, it does not implies f of x is complete. That means under the continuous map, the completeness will not preserve. The question is then when it will be preserved. What should be the condition you can add into the continuity so it will be preserved. So these are the few questions you can ask. Then later on we have discussed that about the function is bounded function. And if you define any function from x to y on a compact matrix space, a continuous function on a compact matrix space. So if f is continuous and x is compact, that will implies f is bounded. F is bounded means a range of the function is bounded. And not only we have proved that it is bounded function, if you have a real valued function, that means if your function is x to r, which is a real value, and it is a continuous with x is compact, then we can definitely say that f is bounded. But it's also we can say that this f attains its bound. That means LUB and GLB has to be exist inside this f of x. And also we have learned that, or we have proved that result is if you have a function which is continuous, which is defined on a compact set, then f inverse is also continuous. That means any function which is defined from x to y, which is 1 1 on 2, and your domain is compact, then that function is homeomorphic function, or it is a homeomorphism between two sets. Here the compactness is essential, that also we have discussed in the previous lecture. Now in this lecture, our objective is to ask regarding this question. That means xn is Cauchy will not be implies f of xn is Cauchy under the continuous map. So when it will be true. Okay. So the answer to this question is, if you know a uniform continuity, which you have discussed for real valued function in your previous semester. So under the uniform convergence, the Cauchy sequence is preserved, not under a continuous. So for that I need to discuss what is the definition of uniform continuous function. So uniformly continuous. So in that, what you have studied in your previous semester is about a real valued function. Here we are talking about the uniformly continuous function on in general any matrix space. So let x comma d1 and y comma d2 be a matrix spaces. A function f from x to y is said to be uniformly continuous. on x if for every epsilon greater than 0 there exists a delta greater than 0. This delta is depending only on epsilon, such that d of xy is less than delta implies, or d1 of xy is less than delta implies d2 of f of x f of y is less than epsilon for every x, for every y in x. So this is a definition of uniform continuity. You have, I hope you have studied this uniform continuity in your previous semester in detail. So here your delta is depending on epsilon. Okay. So obviously one have a note here which says that what should be the relation between uniform continuity and the continuous function. Uniform continuous function and the continuous function. So which one implies which one? So obviously we can say that every uniform continuous function is always continuous. So these are the notes we can write here, that every uniform continuous function is continuous. This is always true. The converse is not true. Okay. Example you can have, that is a function from R to R is f of x is equal to x square if you define, and this is continuous function because of it is a polynomial function, but this is not uniform continuity, which probably you have discussed in your previous semester. Also, we have known that under the continuity, uniform convergence is not preserved. So we have the next result which is based on this concept. It tells you that if f from x to y is uniformly continuous function and xn is a Cauchy sequence, in x, then prove that f of xn is a Cauchy sequence in y. So under the uniform continuity, under the uniform continuous function or uniform continuity, the Cauchy sequence is preserved. So let's give the definition of this. Let epsilon to be given. Let's say this epsilon is given. Since this f is uniformly continuous, there exists a delta greater than 0, depends on only on epsilon. Such that d1 of x comma y is the delta implies d2 of f of x f of y is an epsilon for every xy belongs to x. And since this xn is a Cauchy sequence in X. Therefore, there exists n0 belongs to n, such that for every mn greater than or equal to n0, for every mn greater than or equal to n0, implies that d1 of xn comma xn is less than delta. Since this delta, according to the definition, for every given epsilon greater than 0, so I am just taking delta is equal to epsilon. Now if we can use this statement 1, because this statement 1 is true for any xy belongs to x. So in particular this xn and xm, this result is true. So this will implies d2 of f of xm and f of xn is less than epsilon. See, in the definition of the uniform continuity, whenever it is a uniform continuity is there, it is this delta is depends on x. It may depends on x and epsilon as well. But here this delta is not depending on x. So that's why we can apply that concept here. So this is true whenever this every mn is greater than or equal to n0. So therefore we can say that the sequence f of xn is a Cauchy sequence in Y. So this theorem tells you that under the uniform continuity, the Cauchy sequence is preserved. Still the question about the completeness is left, that you can discuss by yourself or try to find out the answer to that. The next theorem is very interesting, and many a times based on this theorem a NET have asked the question. Let us discuss that theorem. Let x comma d1 be a compact matrix space. And if f is continuous from x into matrix space Y, comma d2, then prove that f is uniformly continuous. What does it mean? If you have a define any continuous function on a compact matrix space, then it is always continuous, uniformly continuous. Any function which is defined on compact matrix space, any continuous function defined on a compact matrix space is uniformly continuous. That means if you have any continuous function defined on a compact matrix space, then it will preserve the Cauchy sequence to Cauchy sequence. Okay, so that is the concept is this, and it will also gives you the regarding the uniform continuity. For example, if I have the function which is r to r, which is not uniformly continuous, we know it is not uniformly continuous over the r, but it is uniformly continuous over the closed interval 0 1 to r. The same function, if I define the same function on this interval, which is a closed and bounded interval, so it is a compact interval of r. So that's why on this interval, this function is uniformly. This theorem tells you that if you have any function which is defined on a compact set, it's definitely continuous, uniformly continuous. So this theorem is very strong theorem, and there are many a times the examples based on this. As I told you, it is asked in the NET exam. So this is one of the way you can check whether the given function is uniformly continuous, rather than finding the epsilon and delta every time. Okay. So let us discuss the proof for this. So as per the given condition that f is continuous, so assume that f is continuous from x to y. Therefore, when I pick up one point, let's take for any a belongs to x, I am picking one a in x, which is fixed. Therefore, we can say that for given epsilon greater than 0, there exists a delta greater than 0, which is depends only on x, only on epsilon, depending on epsilon. This is continuous, so it is depends on not only on epsilon, but it is depends on x and epsilon. It may depend on x also. Such that d1 of x comma a less than delta implies d2 of f of x comma f of a less than epsilon. So it is continuous at a we have taken. Will this adjust this epsilon later on? And I will call this inequalities or this statement as statement 1. Now, let us suppose that the family of all open sphere center at A and the radius is r by 2. Okay, this is for every A belongs to X. Is an open covering of X. So this is, so what we can say is X is a union of, means it is a subset of union of S R. So open sphere I am just denoting in this manner. A is a center, R by 2 is a radius of that. So we are just saying that this all this X in X, A in X will have this open spheres, and which is open covering. And we have know that since X is compact, every open covering has finite subcovering. So since X is compact, this open covering contains a finite subcovering. Say that finite subcovering is A S A 1 R1 by 2, S A2 R2 by 2, up to so on S A N Rn by 2. This is the open covering we have. That means what we have, X is now union of this I running from 1 to n S Ai of Ri by 2. Now our objective is to choose a delta because I want to find out that f is uniformly continuous. So for that delta, so as per the definition of uniform continuity, for every given epsilon there exists a delta. That delta has to be depends only on epsilon, not on x. So for that I am taking this delta will be the minimum of R1 by 2, R2 by 2, up to so on Rn by 2. Whatever the minimum of out of this things. What we will show, we shall show that this delta will satisfy the definition of uniform continuous function, uniform continuity. Okay. Now for any a belongs to x, a will be in, so this the same a we are having, this a we have taken this for any a which is in this, which is continuous, we have given. So it is in this finite union of open sphere. It will be in that S R S A I R I by 2. So therefore we can say that this A has to be in sum of this. So let's say it is S of AK RK by 2 for sum K is equal to 1 to up to n. So therefore what is this gives? This will gives you D of A and AK is less than RK by 2. Okay, this is, I will call it statement 2 or inequality 2. Now d1 of x comma a is less than delta. Now this is the logic where we have why this is minimum is required. This is the logic why we have taken this delta is minimum of this R1 to Rn. This will be the things which we have, because I want to prove that this is less than delta. So I will start now. If this d1 of x comma a is less than delta according to this statement, which will implies this thing. So therefore what we can have is d1 of x comma a is less than delta, and this delta is the minimum of all this Ri by 2 from R1 to Rn. So this means this delta is less than this Rk by 2 because it is a minimum. So this will implies that d1 of x comma a is less than Rk by 2. That means this point A, it is in sum of the sphere. It is inside sum of the sphere. So now d1 of x comma a, I will start with x comma x ak, which will be less than by triangle inequality, not triangle inequality, but just it will be less than this plus, yeah, we are using the triangle inequality here, that is ak. We have did in the statement 2, and if I can say this is inequality 3, so this is Rk by 2 plus Rk by 2. This is because of 3 and 2. So therefore this is equal to Rk. So that means d1 of x comma ak is less than Rk. Now using the statement 1. The statement 1 says that it is uniformly, it is continuous. That is the statement 1. So d2 of f of x comma f of a is less than epsilon by 2 because of this. The statement 1 which we have here, it is true for any a belongs to x. So in particular it is true for ak also. It is true for ak also, because this distance between x and ak is less than Rk. Okay. So as per, if I use that one, that means I can say it is epsilon by 2. I'm just adjusting this epsilon here, epsilon by 2. Okay. And d2 of f of a comma ak, also we can say that this is less than epsilon by 2 due to this statement. A comma ak is less than rk by 2. So as per this delta, this would be the less than, as per the statement 1. Whenever I may write, whenever distance between x and ak is less than delta and distance between a and ak is less than delta, that we have. Now ultimate objective is to prove that distance between f of x and f of a, for any a, this will be the less than delta, epsilon. So by triangle inequality, we can say that this is f of x comma f of a plus distance between f of ak comma f of a. This is less than epsilon by 2 due to this statement number, if I can say 4, and this is less than epsilon by 2 plus epsilon by 2 equal to epsilon. This is because of 4. When this means distance between this x comma a is less than delta, where delta is minimum of r1 r2 up to rn. It only depends where delta is minimum of r1 by 2, r2 by 2 up to rn by 2, which depends only on epsilon, or I can say it does not depends on x. Therefore, f is uniformly continuous. So there was, I'm interested to discuss one of the problem which is asked in one of the net exam, many of the net examination, not one, many. The same kind of question was asked. So let's have the question. F is continuous on close interval 0. Then okay, let us rephrase the question. Which of the following functions are uniformly continuous on open interval 0? The options are given is this. First one, 1 upon x. The second one, sin x. Third one, sin 1 by x. The fourth one, cos 1 by x. What is your answer? So which of the following functions are uniformly continuous on this open interval 0, 1. Any answer from you guys? What about the statement 1? Means what about this function 1? Is this function 1 is uniformly continuous? And this is the 4. What is the question's marks? It is 4.75, which is in part C. The question was asked in part C of the NET examination, and having the marks is 4.75. So can you tell me? So it may be possible that one option is true, or you have one of this function is uniformly continuous, or two of this function is continuous, or all of them is uniformly continuous. It is depends. What about the first function, which is a uniformly continuous? Can you say that 1 upon x is continuous on this open interval 0, 1? You guys are there? What you can say? Is it continuous on open interval 0, 1? 1 upon x?
Yes, sir.
In fact, this 1 upon x is continuous on r minus 0. So except 0, it is continuous. But this function is not uniformly continuous. I will give you the reason. Because if you have epsilon, which is 1 by 2, if I take epsilon as 1 by 2 and take your n is greater than 1, such that 1 upon n is less than delta. Let this x1 is 1 by n and x2 is 1 upon n plus 1. This x1 and x2, both of them are in the open interval 0, 1. And the distance between x1 and x2, which is the absolute metric, 1 by n minus 1 upon n plus 1. This will, I can say it is less than 1 by n, so this is less than delta, as we have taken your n is in such a way. But what is your f of xn? But mod of f of x1 minus f of x2 is 1 upon x1 minus 1 upon x2. As per this, x1 is 1 upon n, f of xn, that is 1 upon x1 is n, minus, as per the same argument, it is n plus 1. And this will gives you equal to 1, which is greater than epsilon. Here we have taken our epsilon is 1 by 2. So this is gives you a contradiction. 1 by 2 is greater than 1. So therefore, f is not uniformly continuous. Open interval 0. Okay. Why this is happening? Why this is happening? Because when I include this interval, closed interval 0, 1 here, then this set is compact set. And on this compact set, or I can say the limit point of this open intervals are 0 and 1. They are the limit point, which is not in that set. If you include at that limit points into this set, and on that set, if your function is uniformly continuous, if your function is continuous, then you can say that that function is also uniformly continuous. So if I include this limit points, all the limit points of this open interval 0, 1, still this function is not continuous on this set. So that's why this 1 upon x is not uniform continuous. But this sin x is uniform. Why? Because when I include the limit points of this set, which is closed interval 0, 1, and on this closed interval 0, 1, sin x, we know it is continuous. And so it is uniformly continuous. The same argument can be given for sin 1 upon x. Sin 1 upon x is not continuous on this interval, and 0 is the limit point of this. So that's why this is not uniform continuous. No need to find out every times, no need to calculate this epsilon and delta. And the same argument is given for the question, means this fourth option. This function cos 1 by x is not continuous at 0, which is a limit point of this set. Okay, so in that manner, or in this argument, you can establish lots of things here. So this type of examples they have asked in the NET exam. You can